Yes, welcome back. Now let us see the implementation of combinational circuits. The implementation of combinational circuit on CLBs mainly. So CLB means I said using lookup tables. The realization is using lookup tables, and also I said that the lookup table includes RAM unit and also multiplexer unit. Okay, so let us see the implementation first of all with one input combinational circuit. Okay, so actually this lookup table implementation is based on the truth table. Okay, lookup table implementation is based on the truth table. So for one input combinational circuit case, let us see how to develop the truth table. Okay, so since it has one input and one output, so for zero input, let us suppose the output is f of 0. Okay, so and for one input the output is f of 1. Okay, so what is that f of 0 value, f of 1 value? Now we don't bother about that one. Okay, so with the 0 input the output of f of 0, with one input the output of f of 1 is the output. Okay, so with this how to realize means, in the realization case what I said, it lookup table includes RAM and multiplexers. Okay, now the size of RAM here is 2 locations, 2 1-bit storage units the RAM has. Okay, because 2 outputs with 1-bit data, so the RAM includes 2 locations, each location can hold only 1-bit data. Okay, so followed by a multiplexer. Okay, followed by a multiplexer, that is here the RAM size is only 2, so a 2 input multiplexer we need. Okay, 2 input multiplexer. Okay, so 2 input multiplexer means one select line, it has one select line. Okay, let us see the generic structure of that diagram, that is this one. So what it is, okay, this is the RAM, okay, the first block of RAM holds f of 0 result, the second block holds f of 1 result. Okay, so 2 inputs, these two are acts as inputs for the 2x1 multiplexer. This is the multiplexer with one select line, okay, so that select line is usually input variable x, and one output is the output variable y. Okay, suppose if the input is x, so f of 0 is connected to y. Suppose if the input is 1, f of 1 is connected to y. Same thing. So if you observe here in the truth table case in previous slide, if x is 0, what is y? F of 0. If x is 1, what is y? F of 1. Okay, clear? So like that the lookup table with RAM and multiplexer can be implemented. Okay, so which circuit is the one input circuit? That is NOT gate circuit is the one input circuit. Let us see the realization. So this is the realization of the NOT gate using DSD UNIT. Okay, that is so with okay, let the RAM consists like 1 0. Okay, and this is the multiplexer, the output is x, y equal to x bar. Okay, if you first of all what I said, you have to prepare the truth table for the given function. That is y equal to x bar is the function. Okay, truth table is, if x is 0, the expected output is 1. If x is 1, the expected output is 0. Okay, so like that you can implement or you can you can implement on LUTs. Okay, on LUTs. Okay, is it clear? So better before going to draw this one directly, you prepare a truth table for the NOT gate. NOT gate, one input x, another input is y. X is 0, y is 1. X is 1, y is 0. Like that you plot the truth table first of all and place the output, whatever the output information is there, that in RAM place that information in the RAM, and the select input is the actual input in the given function. Select input in this realization is the here the select input is as per the function the input variable, as per the function the input variable. So x is the input variable, y is the output variable, and RAM inputs the result of the function. Okay, so that the realization can be done. So let us see, this is the one variable implementation. Similarly, two variable implementation case, the generic truth table is like this. The generic truth table is under two variables, four possibilities are there. Under two variables x, y, four possibilities 0, 0, 0, 1, 1, 0, 1, 1. Okay, therefore the output z is based on the given function. You may get the values. Okay, so here in first of all f of 0, 0, first value is referred as f of 0, second one is f of 0, 1, f of 1, 0, f of 1, 1. Whatever the based on the function the value depends. Okay, but first output is f of 0, 0, that is with the inputs are 0, 0, what is the value that value you have to load here. Okay, and the generic implementation diagram is like this. So four inputs we have now, four inputs, that is actually from the table. What is the RAM size? What is the RAM size? 4 locations. 4 locations acts as an input for the multiplexer. So 4 by 1 multiplexer you need to take, 4 by 1 multiplexer. When the inputs are 4 in case of multiplexer, 2 select lines are necessary. So this is the generic implementation of a 2 input combinational circuit. 2 input combinational circuit. Okay. So as per the truth table, 4 bit RAM we need to have. So those 4 locations acts as a 4 inputs for the multiplexer. Therefore the multiplexer size is 4 by 1, hence its select lines are 2 only. Okay. Suppose if the select lines are 0, 0, f of 0, 0 value is connected to z. If it is 0, 1, f of 0, 1 value is connected to output. If it is 1, 0, f of 1, 0 value is connected to output. F of 1, 1, x is 1, y also 1, f of 1, 1 input is connected to this one. Okay. So suppose with reference to two variable, if the given function is like this, the given function is OR gate. In OR gate case, 2 input OR gate case, based on the truth table, the outputs are 0, 1, 1, 1, right? Based on the truth table of OR gate, the outputs are 0, 1, 1, 1. So that data you need to load in the RAM first of all. Okay, that data has to be loaded in this one. Okay, so after that I said that the select lines are the actual function inputs, actual function variables. Okay, function variables are x, y. So x is one select line and y is the another select line. Okay, if both x is 0, y is 0. Okay, as in here also you better to plot the truth table. Okay, you better to plot the truth table. After that you can see the implementation using this 4 by 1 multiplexer. Okay, similarly here the slide also shows the implementation using for AND gate and XOR gate also. Okay, so if you observe the RAM data is the result of the OR gate. Okay, result of the AND gate and result of the XOR gate for all combinations, Okay, since two variable means 4 possibilities, in each possibility what is the output, that output is loaded in this RAM, isn't it? Okay, so if you observe, this is the XOR gate output, this is the AND gate output, this is the OR gate output. Okay, so the output value has to be loaded in the RAM. Then the variables acts as a select lines for the multiplexer. So like that the lookup table realization will be there in the CL base. Is it clear all of you how to implement one variable functions on LUT? What is the size of RAM and what is the size of multiplexer and how the realization can be done. Similarly, two variable functions. Two variable functions on LUT. Okay, two variable functions or LUT can be implemented using 4x1 multiplexers. 4x1 multiplexers that so far I have shown to you. But this also can be implemented using 2x1 multiplexers. Using 2x1 multiplexers also you can implement, but first of all see how to realize the same thing using 2x1 multiplexers. 2x1 multiplexers. So for that one, the generic truth table of two variable function can be divided into two parts. Can be divided into two parts like this. With x0, with x input 0, this is the first part. With x input 1, considered as the second part. Okay. So the first part is at x is 0, whereas in second part at x is 1. Okay, like that each part is divided. Now the first part is realized by 2x1 multiplexer. Similarly the second part also realized by 2x1 multiplexer, and finally using one more 2x1 multiplexer the result of two variable output can be obtained. Okay, so let us see that structure first of all. The structure is like this. The structure is like this. Okay, so all are 2x1 multiplexers. If you observe here, all are two variable multiplexers. Okay, so how the truth table is divided? Based on the x value. Based on the x value. That's why the second level of multiplexer is having the select input is x. The second level multiplexer having the select line is x. Whereas in the first level, not line, in the first level, that for the 2x1 multiplexers, the select input is y. The select input is y. Okay. So based on the y value, one of these two inputs is connected to next level. Similarly, based on the x value, one of its second level inputs are connected to the z. Okay, so that the connection is f of 0 0, f of 0 1 is the first multiplexer inputs, f of 1 0, f of 1 1 are the second multiplexer inputs. Okay, so what I said, based on the x0 case, y0 y1, and simply just whatever the way you divided the truth table, like that the multiplexers can be connected. Okay, first level consists two multiplexers, since the truth table consists two parts. Okay, two parts. This is the first part and this is the second part. What are the function values in the first part? F of 0, f of 0 1. Second part f of 1 0, f of 1 1. Like same you connect like this, but in the first level case the select line is y. And coming to second level, in second level case again with 2x1 multiplexer, but the select input is x. Okay, so like that the realization can be done. Okay, is it clear all of you? Okay, how this is implemented with 2x1 multiplexers. Okay, so now I am going to stop this one. You can implement all our two variable functions which I have shown in the previous slide, like OR gate realization, AND gate realization, and XOR gate realizations using these 2x1 multiplexers. Already 4x1 multiplexer I have shown, but now you implement. I have given the general structure how to implement the same using 2x1 multiplexers. Okay, for those three gates you show the result, lookup table realization using 2x1 multiplexers. Right? Thank you.